Okay, good evening everybody. Can anybody hear me? Let's see the live chat if my audio is coming through. Can anybody hear me? Yes, okay, great. Awesome. Well guys, today we're going to present the data that we've gathered last weekend on the force to level measurements. We haven't compiled a complete analysis yet because there's an enormous amount of data for us to go through, and we want to make sure that all the calculations that we do and the data that we select to use is actually the good stuff, and that we're able to draw definite conclusions from it. But in order to give some openness, or at least some insight into what we've gathered so far, I thought it was a good idea to to actually go through what we've gathered and draw some initial conclusions from it. It's not like they're binding conclusion, because a lot may change. For example, we haven't actually calculated in the forced line itself yet. We just have the differential leveling sorted out. All the atmospheric data is not in the actual display that we're going to show today. So that's something that is going to be in the next phase, because we want to see if there's a correlation between the actual measurement data that we've gathered and, for example, ambient conditions from the weather station. So without further ado, I think it's better to give Sandor the word so he can share his screen and give a rundown to what we've gathered so far. Sandor?
Yes, I will pull up this now. I'm very happy about this measurement because we gathered really a lot of data and very high precision data. So as you said, actually for each measurement, just let me show you another screen before this. For each measurement, what we are doing, you see my screen with the rods?
Yes, we do.
You do, okay. So for each measurement, we have 3 positions that we are measuring back and forth 4 rods. That means we have 12 sets of measurements for each measurement position. And we have to choose which one we use for the force line. That's why we are examining the data that we got from all these measurements and looking for which one is the most reliable data in terms of precision and probably no errors. So for example, here we have position 1. We are making readings on A1, B1, C1, and D1. And then we are also moving our rod to the 3rd position where we are measuring also these 4 rods, and then to the middle position.
Can I just clarify for everybody that's watching this that the first position is between A and B, and not like this image showing that we start between B and C. The first position is between A and B.
Yes, exactly. That's here. So we have these 12 sets of data, and for the moment we see that we have the best data, which was taken from position 1 to rod 4, which is D1 here. And as a counter measurement, position 3 looking to rod 1 or A1 in this picture. This gives us the best resolution also, and this is what we are going to set up the force line with. And we will also set up a control force line, which will be the measurements from P2 position to rod 1 and rod 4, which is A1 and D1 here. So with these data, we see that really the resolution is so high that we can even see small amounts of differences in this level, like to the 1/10,000th or even better. Let's go back to the other screen. So in high resolution, we can see these lines, that they are not in a perfectly straight line, but let's say they have these little bumps up and down, which is random, and it doesn't give us a trend for a curve, for example. It's just randomly going up and down in these minute scales. And then we have these high peaks, which seems to be not really a measurement result, but maybe it could be a measurement error. As in this leapfrogging technique, we are turning the rods, and by that turning, it might be that something dirt or something gets underneath the rod, and then we measure like a peak here, which is still only 0.16 of a foot. So that's the peak what we see here, for example. We will investigate what these peaks are really meaning, if they are really geopotential surface measurements, or we had any type of problems with the wind shaking the rods, for example, or turning the rods that could introduce an error there. But if I take out all these high values that let's do it this way, that I marked here on the left, this is actually what we are investigating now, then we can bring the scale down to the very finest precision. This is what we see with the real geopotential surface. So now, So now we are down to 0.002 feet accuracy or measurement steps. You can see that this geopotential surface looks like to be going down and then up again, down and up again, all through the distance. Actually, this is what I expected. So I think when we are looking at something which is a smooth surface, and we take a microscope and we look into it in a higher magnification, then we see that this smooth, flat, or whatever surface is becoming bumpy. And exactly that's what I'm seeing here. It's an overall flat surface, which is bumpy in this magnitude of 0.02 feet.
Yes, well, of course, we still have to check. You know, all these numbers in the graph represent a measurement precision, and we still have to check. You know, for example, what the ambient conditions were with every measurement. And we also had some issues with the weather itself. On the first day, they had to you know, take a break halfway. I think around noon, you know, then it started to rain, so they had to pack up the gear and you know, go to a restaurant and then come back 2 hours later and proceed with the measurements. You know, and that could also introduce this error that we see.
Yes.
Also, there was occasions that the wind was actually increasing above the you know, the limited threshold for the rods to, you know, to keep standing still, or at least not vibrate in the wind or actually fall over. You know, and we've had a couple of incidences where that actually happened, and that is also a possibility that could cause those spikes in the measurements.
Yes, actually, this is the end of day one between these measurements. So it looks like that the weather or the end of day one seems to be a peak there, and this is the second day in the beginning. So it could be also when they restarted the measurement, some conditions were completely different. Because here on the first day we had rain, second day it was rather windy. And as you said, Mike, that even a small resonance from the wind can give us errors in this magnitude of 0.002 feet.
Yes, exactly. And you know, just for argument's sake, and maybe you can draw in the actual expected drop that was supposed to be there in reference to the actual lines.
Yes, these are the calculated curvature drops on the GE model. And if we plot that, measurement 1 should be here at 0.005. Then the next one is at 1000 here. Third one is 1600, which is here. And then 2500, which is here. So we can see that the curved surface of the globe model should be way much higher in the measurement results, even at the very first positions. And this is a squared curve here, so it should be like exponentially rising up from the fifth measurement upwards. You can see that even at the highest peak here at measurement 7, we are at the curvature rate, which should be at measurement 3.
Yeah, but you know, just a reminder for everybody that you know, the zero line in this case does not represent the forced line. You know, that's still something that needs to be added in. So the actual line that we're measuring, you know, the measured line versus the forced line, may give another picture than what you actually see on the screen right now. So you know, that's what a bit of a disclaimer, but you know, I'm not expecting there to be an exponential curve in any direction, because there's no indication of that in the current graphs that we see on the screen right now.
Exactly. These ups and downs are totally random, and they don't seem to follow any kind of mathematical model, so not even a curved surface.
No, and I think on these measurements, we set the digital auto level to not compensate for something that we're trying to detect, which was a feature that was turned on in the preliminary test we did in September of last year. You know, and in that result, we ended up with with an exponential curve going in the opposite direction of what you should expect. And the reason that was the case was because of the settings of the digital auto level, and now we've set everything up as it should. Now the device was calibrated, and we did it with a lot of redundant measuring. Now everything was done in triplets, and the fact that we have these spikes at measurement 7 and measurement 9 and 15 is something that we still have to investigate. Now there's still a ton of data that we need to graph out in the same fashion as we did here. You know, the atmospheric conditions, temperature, wind, humidity. You know, and if they show similar spikes, for example, then we might have a correlation as to why these values differ so much from the rest. But as I said, it could also be down to measurement error, and we recorded the entire day, both days, so it's easy for us to find out if there is anything happening at those measurements themselves. You know, we just have to rewind back to the live stream and just watch if there's something going wrong, or there's a break at measurement 7 or measurement 9 and measurement 15.
Yes, because these numbers seem to be indicating a really high change compared to all the others. It's fascinating how precise our measurement is. I'm sure that it has never been measured so precisely with any type of measurements, like These satellites can go down to maybe centimeters, but not more precise. And we are actually down to 10,000ths of a foot precision. So I think this is really the way how this geopotential surface can be measured in the highest resolution.
Yes, so we're fairly happy with the result. As I said, we still have to do a lot of work with all the data. You know, these are just the numbers you're seeing on the screen. There's they can give us a pretty good indication as to what we might expect as an end result, but we still have to do we still have to do some additional data analysis to actually come to a definite conclusion. We have to, as Sander said, there are a lot of redundant measurements, so we can actually choose which ones are the most reliable. Because everything has a reciprocal shot. The unbalanced shot from position A1 to P1, from P1 to rod A and 4. That's an unbalanced shot to the closest one and the most distant one. Normally, in surveying, the unbalanced shots are useless information, but since it's a reciprocal shot, or at least a mirrored shot from position 4 back to the same rod, those should give a similar result. And that's what the digital auto level actually did. There's maybe a 10,000ths of a couple of 10,000ths of a foot differences between the actual measurements, but they seem to be how do you say that, perfectly mirror images of each other. So those seem to be reliable data points that we can actually use to extrapolate the forced line. But we also have the P2 position, which is basically a combination of balanced shots between the closest two rods and the two most distant rods, and those are balanced shots, so we can compare those to the unbalanced. And that's why, as I said, there's a ton of stuff for us to go through and see what we can use best as most reliable data. And once we've done that, we will compile it into a nice document and put it up online for everybody to scrutinize and maybe even repeat, because Chris was kind enough to put steel spikes in all the measurement locations on the strip of land that we actually used. So anybody that wants to replicate the measurements can just go there and use the spikes that are still in there. So yeah, I think we did a pretty good job so far, and we will see where the actual end result goes. But I think this already gives a pretty good idea as to what we can expect from the actual final conclusion.
Yeah. Just to add here that these numbers here on the left, they are representing the measurement lines, but they are all put together at 0.00 on the B log. So this is how we can define, because all these measurements were done in a different height. So now we transpose them to equal height at B position, at B row. That's how we end up with all the zeros at the B row. And A and D is representing the furthest on the two sides. And you can see here that these numbers, even if they peak out the 0.1537 or the 1558, they are nearly the same. And that's like representing also that maybe these peaks are real geopotential surface, because we measured it both ways, back and forth. So these are all the things that we have to figure out, especially depending on the weather data, because we see really interesting anomalies in these numbers at these positions that you mentioned already.
Yeah, we went, or at least Chris and then the team went out of their way to document everything visually on a written record and on a digital record. So now we have tons of redundant data, but actually putting everything together in your spare time, it will require some time for us to actually go through every single measurement, and there was a lot of that. As I said, every measurement also has ambient conditions from the weather station attached to it, so that is also the data that we have to timestamp and place under each measurement, so we can actually see if there's a correlation between ambient conditions and what we're actually measuring.
Yes, exactly. So we'll do that in the next upcoming days, and we hopefully get soon answer soon. And I'm really happy to work with these data because they are so interesting, and nice to find out what's really happening out there.
Yeah. Well, I think we only got to instead of 2 miles, I think we got as far as 900 meters. Because it's a very labor intensive process, and there's also a great deal of communication that goes along with that. Documenting everything and requires a camera team to walk back and forth between all the rods. So it was very time consuming, and we were hoping to get to 2 miles, but as with most of our set goals, they're over ambitious, and now we know that we need to speed it up to actually go an extended distance. There are still some improvements that we can add to the method itself as it is right now.
Yes, compared to the 3-rod version that we did last year, this is actually 4 times more work, because we have 4 rods, 3 positions, and we had only 1 position with 3 rods. So we are really gathering a huge amount of data here.
Yes, and now Robert and Karen were actually there during both days, and maybe Robert can tell us something about what actually went into the practice of doing the measurements themselves.
Sure. Can you hear me?
Yep, we can.
Okay, great. One thing I wanted to point out as I was listening to Sandor's explanation and everything, and I'm, looking at the numbers kind of puts me in a daze there as to what we're actually coming up with. But now I can see that, so of the rods A, B, C, and D, that B becomes the reference point. The gravitational potential at that point, we'll say that is what we're going to call perpendicular to the surface, or plumb. A line would be exactly straight up and down there. And now we're checking how A, C, and D vary from that. So that's good for me to understand that thing. Now, on the actual day, it took us a couple hours the first day to really get the rhythm right. If you think of the setup, you have 4 rods, that's 4 people. You should have 1 person per rod to make sure to be right there and make sure it's level, to set it level, then to change it. And they should be staying there all the time. So exactly when the surveyor, which in this case was Chris, with the auto level, is ready to take the measurement, that all he has to do is wave to the person, and the person gives a thumbs up, because that tells the person at the rod that I'm ready to measure you. Is the rod ready? And it shouldn't be any delay. It shouldn't have to say, hey, And so the first day we had people enough to do that, but the second day we never had enough people to have 4 people at each rod. We ended up having one guy that walked with us that is a surveyor also, so he knew how to level it and very efficiently, and he was attentive to what Chris was needing. Each time you change the position of the auto level, you have to re-level it, and he has to make measurements 180 degrees, then 90 degrees from that beginning point to make sure the rod is level in all directions, or the auto level is actual level, and then start its measurement. And the actual, when you point it and the auto level has it focused in on the rod, he punches a button, say measure, and it's about 20 seconds before the numbers come up. And he does that 3 times to see that he's getting a good, consistent reading. And that's the first time that he can write down the numbers. The person next to him can type those numbers that he's written and he's calling out into the database, into a spreadsheet that's on a phone, you know, a handheld device. And then we have another person that comes and takes, the first day we had 2 people, one with each one with the phone, that took a picture of the auto levels readout, and then would take a picture of the ambient weather conditions from the weather station that was right next to the rod. So that would be the optimum number of people: 4 for the rods, 1 for the auto level, 1 taking the data of the auto level, so we're up to 6, 2 people taking pictures of both the auto level and the weather station. That's 7 and 8. A third person to move the weather station readout, and that's 9. And then a 10th person that does more walking than anybody is to move the weather station collection point. So every time you make a measurement, that weather station readout collection point, the actual, you know, anemometer and equipment that's there, is connected via Wi-Fi to the readout, so you can move it 120 meters away through the good, very powerful signal. And so he would have to move a minimum of 40 meters between each measurement. And then once he's got down to rod 4, or, you know, A, B, C, and D, measurement on D, then he's going to have to move 120 meters, 3 rods down, to start the new rod A. And so he's there's time waiting for that. I measured when we were at our most efficient functioning that it took about exactly 2 minutes between readings. Bob Nodal was there on the second day, and he would call off the exact time that the reading was received as he read it, as soon as Chris would finish with the numbers. And it was 2 minutes in between when we were going as fast as possible. Then you have movement of the weather station, movement of the next, the auto level goes to the next reading position in between rods C and D. That takes about 5 minutes, because you have to walk down there, easily 2 minutes or 3 minutes, and then you have to set it up, and Chris tamps it down. Each one of those things, he actually jumps on it with his foot on each of the 3 legs of the tripod, even though he's on cement, to make sure it's very stable. And then nobody touches it other than him to swivel the head, and nobody touches the tripod for the next 4 measurements. And so that takes at least 5, and then he has to level it. He has to take 4 looks through the oculus and sees it in 4 different directions in order to verify that it's level, and make adjustments too. So it's a minimum of 5 minutes for that. So you've got 4 measurements at 2 minutes, 8 minutes, plus 5 minutes, and then the weather station moving to, basically, realistically, the fastest you can go is 15 minutes for 1 position measurement. So that's 4 different readings plus the setup. So it'll be 15 minutes in between those. And there's 3 of those per location. So it takes 45 minutes to move 40 meters, where you take the leapfrog, we call it, moving rod A now to the new rod D position. there's a minimum of 45 minutes between each of those moves. So that's how long it takes. And frankly, on day 2, we were short by at least 3 or 4 people. And there's one person taking 2 cameras to take pictures and moving the weather readout point. So it was difficult, and there wasn't somebody always right there at a rod. And so someone would have to run over to the rod when Chris would yell, "Hey, I need somebody to check the level there." And then sometimes it had to be changed because they hadn't been there. So that slowed everything down too.
We also had issues with wind and the weather knocking the rods down repeatedly. So we had to deal with that as well.
Yeah, and at one point, one rod had fallen over 3 times in a row and hit itself on the cement sidewalk. And so Chris had to go and verify that it was level with the auto. It just was about 20 minutes worth of, at least 15 minutes worth of work, just make sure that what the rod was still straight and that the bubble was still giving a correct readout, at least in the direction we needed it to be. So yeah, more manpower would have helped. And I guess also the weather did not cooperate perfectly. We had low, small clouds. And yet they were still dropping rain in various directions from us. And then sooner or later, one of them came right over the top, and that forced us to stop. When the rain's coming down, the winds increase, and we don't want the auto level to get all that wet, or any of our equipment really. So that was difficult. We also had time-lapse cameras that needed to be moved, and I did most of that. But so a lot of effort to try and record and keep track of everything, and yet keep moving.
Yeah, you did a great job. I was following it all the 2 days, and I'm really proud of you. So it was fun for us to watch, and probably very difficult for you to manage.
It was okay. We just, you had so much to do. We were motivated, but we were out 12 hours the first day and 8 hours the second day.
Yeah, it was just a learning curve, just because it's the first time we've done something like this of this scale, and everybody involved was new to it. So we had to get everybody on the same page, and that took a few different tries to do. But once everybody got it, there was a good rhythm going. But definitely the weather is a factor, and not everybody being able to be there both days, all days. And so that's what we dealt with. But I think we got pretty far for what we had to work with.
Yes, actually the measurement distance that I'm dealing with the data with is 900 meters. It's almost 1 kilometer. This measurement is also representing only that surface. So we are not extrapolating it to the whole world, but definitely some other measurements should be done anywhere else. But this 900 meters, I think, definitely proves that area there. And as I said, it's such a high precision that you can even see those tiny little bumps in the geopotential surface. So even if you did the 2 miles, right, that we planned, I think we would just have the similar effect going on and on.
Well, it's exciting. It's exciting to me because I don't care where you look. If somebody can show me someplace in the whole world where there is data of checking the geopotential. Now, the geopotential is the direction of gravity compared to the ground you're standing upon. And so the geopotential should be perpendicular to any body of water. And if you check what the slope is of the ground you're on from point A to point B, then the geopotential should be should be level. to that particular location, no matter where you move, it should be level. If you straighten out the ground, but based upon the slope, you figure out what the slope is of the ground. So between point A and B, for example, we've got 40 meters. And if it goes down 1 foot, and in the land we were on varied significantly at points. It was a walkway, but it wasn't by no means straight. When we were about done with the second day's location, we'd started out at one stoplight, and we had moved towards another stoplight along Tower Road. It was 1 mile apart, the stoplights were. But by the time that we were about 3/4 mile down, you could barely, just above the changing elevation in the ground, you could barely see stoplight 1. I mean, you could see the boom going across there, but it was low to the ground because we were going uphill and uphill and then back downhill. So it wasn't a completely flat, perfect place. And I don't know if you could find one that was flat. You're seeing things change so much there. Of course, perspective is going to make it look lower too as you go farther away. But if you know exactly what your slope is, then you can, your numbers will come out to show you what was absolutely level. So rod B was selected to be the level. That's straight up and down. And then the other rods, A, C, and D, were able to be shown to be slightly off kilter, okay, slightly off of the same degree of plumb, they were no longer parallel to the location at rod B as far as being perpendicular to a totally flat surface, a non-sloped surface. And so to say, well, you should have done it over water, I saw somebody say, no. First of all, you can't do this measurement over water. You've got the water that's going to go up and down. You need a very firm surface to have an exact height location. And secondly, this is the point of the auto level checking the different heights, and then that's eliminated through the calculations. And so we are having one continuous line that is level, and then we compare what the actual height changes are that is added to that by any tilt, by any angular difference of what we think is perpendicular, what is perpendicular at that point, the geopotential. That's what I'm trying to say is the actual gravitational direction at rod A differs than the gravitational direction at rod B, C, and D. And by how much does it? And what we found out is that it measures it changes very slightly. However, there's no trend which would be present if there was an overall continuously changing geopotential as stated in the WGS 84 model of the Earth's surface. We found some changes, and what's exciting is rather than saying satellites, quasars, what else? It's all space-based things from millions of miles away, trying to measure something that is literally at our feet. And I think this is the first time in history that we know of that we've been able to come up with a way to actually physically measure on the surface any changes in the geopotential, that gravitational direction from point A to point B, literally 40 meters apart and then up to 120 meters apart. So it's very exciting to me, very exciting.
I like to show this force level experiment like we are building a bridge. The bridge has to be flat. That's the only parameters for the bridge that you have to follow, like we don't care about weight and so on. But we are not actually building this bridge, we are only lining it out how this should look like. And therefore we get a perfectly perpendicular flat baseline on the starting position. And then we can measure the tilt, as you said, Robert, or the height, which is correlating at each position. But we are not measuring the topographic surface, so we have these 4 rods to calculate what actually the topographic part above the geopotential surface line.
Yeah, that's right.
Okay,
So-
well, no, I think that about sums it up what we've got so far. As I said, we still have to analyze much of the data and put everything together and make a good selection, and then I think probably in about 2 weeks we'll be back with an actual report to to draw conclusions from. So bear with us while we dig through the data, and as soon as we have something news to report, then everybody will hear from us again. I'll probably hear on the live stream. So that wraps it up for me. Does anybody on the panel have anything to say before we close it down?
I'd like to say thanks to everybody that came out and volunteered and helped, especially a man named Lockwood, who was 71 years old, and he drove up from Texas and he hauled that weather station up and down that road. He probably walked more than anybody. So thanks to him and everybody else that came out and helped.
Absolutely, yeah. It was a pleasure to see that there were so many people that were actually willing to help. Okay, guys. Well, thank you for joining, and we'll see everybody soon again, I guess. That's it, guys. See you next time.
All right. Take care, everybody.
Bye-bye.